in the microscopic world. What we have realized, and this is particularly true for the last century, in the 20th century, is that the correct framework, the correct language to describe nature is mathematics, right? So GR, of course, you think about Riemann Einstein's theory of differential geometry. Quantum field theory should really be thought of in terms of an algebraic geometry and group theory. And of course, there have been various proponents. All these people are Nobel Prize winners and Fields medalists over 100 years or more in just trying to capture this fundamental language and understanding of nature. I'll probably end up talking a bit later about this. I'm very honored to have written, to have co-edited this book with Xian Yang. He's 94 now, on this book called Topology of Physics, which was just published last year, in which we invited all of these greats, living greats like Atiyah, Penrose, and Witten, to try to have this dialogue, the most recent dialogue from these grand masters of what is relation between mathematics and physics. So what is the greatest challenge to science, in the opinion of many, is the fact, we've gotten down to 2. Well, it would be really nice if we got it down to 1, right? That's obviously true. Why have 2 sets of equations when you can do 1? And these 2 sets of equations, I emphasize again, are very succinct. You can buy mugs and T-shirts about it. General relativity fits on 1 T-shirt, and the standard model fits on 1 mug. In principle, every interaction in our observable universe can be derived from these 2 equations. So it'd be really nice. Okay, the derivation may take thousands of pages, but it's the principle that counts. The problem is Einstein himself thought about putting these 2 equations together into a single unified equation, which he called the theory of everything, which of course, there's a movie about it. Stephen Hawking spent most of his life working on this theory of everything. Unfortunately, it's hard. Okay, just technically hard. It's a mathematically difficult problem, and it's called the unnormalizability of gravity. And the problem is, if you just put an addition sign of this Lagrangian to this Lagrangian, you're going to get an uncancelable amount of infinities. So it just mathematically is somehow we don't have a nice framework to make this work. So fine. It would be much more satisfying if there were a single equation which unifies the laws of nature. And this is not just for aesthetic reasons, because we know at some point these 2 equations must have unified, in the sense that in the beginning of the universe, or in the inside of a black hole, at the moment of the Big Bang or the moment of the Big Crunch, and we know gravity and quantum field theory must come from a single unified framework, and we don't know what it is yet. So this has been researched since at least the 1960s and 70s. The universe, of course, gives us a very nice hint. It gives us this length called the Planck length. So if you have the fundamental constants of nature, Planck constant, h bar, for quantum mechanics, G Newton, the Newton coupling constant for gravity, and C, the speed of light. This one combination, it's a unique combination. You can do this by dimensional analysis. Gives you around about 10 to the minus 35 meters. Now, somehow, the universe must behave fundamentally differently around about this length scale. We don't know what it is yet. Just to give you a scale of comparison, our current experiments in CERN, which is the best probe into small distance scales, can measure about 10 to the minus 18, 17. So this is 19 orders of magnitude smaller than anything we have ever observed. But the universe must behave differently in this scale. Something must go wrong. So the structure of space and time must break down. And around about that scale, the fundamental laws of physics must unify in this new, completely broken down concept of space and time. So fine, what people thought about in the 1960s and 70s was that, well, let's have, whenever there's a scientific challenge here, Einstein's theory, Einstein's dream of the theory of everything, there must be a paradigm shift, right? This is what philosophers call paradigm shift. And so, one thing obvious to do is that, well, why not go way back to Democritus, the Greek philosopher? We're sort of biased into thinking that fundamental constituents of nature are point-like particles. This is why we call them particles. But instead of that, how about having a small length, a small smeared point, if you wish. What's a smear point? It's called a string. And this is where the word superstring theory comes from. How big is the string? Is around about the size of this 10 to the minus 35 meters. Okay. So this is not a talk about string theory. So this is just sort of motivate where this tradition comes from, all the way from Newton to Einstein to string theory, which is sitting in the tradition of trying to unify space, which technically attempts to unify space-time and quantum gravity, but also philosophically tries to unify mathematics with the language of physics, right? So this is where the tradition comes from. So at this point, let me summarize. Whatever this theory is that came out from the 70s and 80s, is that it's a theory of everything, this string theory, and it proposes that all fundamental particles, quantum field theory itself, are just different vibration modes of an open and closed string, so small that we haven't observed yet. We hope one day, perhaps in the center of a black hole. Now we know that there are black holes in the center of our galaxy. We hope to see this one day. And in addition, this is a theory that obviously, so this is a theory of gravity, and it is also a theory of quantum mechanics. So it unifies a general relativity with quantum field theory and of the standard model. The details I won't get into, and this is sort of realized in the mid-1980s. Mid-1980s. There is, of course, a caveat, because if this theory just worked and it was all great, and there will be no more the entire field of theoretical physics working in this direction will be out of the job. There is, of course, the caveat, and the caveat is that this theory, this promised unified theory of everything, only works in high dimensions. And one of the realizations of the equivalent formulations of the theory is that it only works in 10 dimensions. Now you may wonder, okay, we don't live in 10 dimensions. It's pretty obvious we live in 4 dimensions, and Einstein pretty much settled that, right? We have 3 dimensions of space and 1 dimension of time. So whatever this unified theory that physicists promised all of us in the 1980s is that, well, there's this great promised theoretical conjecture theory in 10 dimensions, which unified everything. But we don't live in 10 dimensions. We live in our world, which is a 3 plus 1 dimensional world of space-time that has quantum field theory in the microscopic scale and general relativity in the larger scale. So we got to do something about this. Well, this is not a particular challenge to theoretical physicists. See, because you have to do just to take the extra 6 dimensions to be something else, right? So there are 2 ways of understanding these extra 6 dimensions. One of them is called compactification, which is just the proposal that these extra 6 dimensions are so small we haven't seen them yet. And that literally is like every point in space-time has a curled up tiny little dimension, or not 8 dimensions, 6 extra dimensions, right? Another way to see it is we are trapped in a 4-dimensional slice of this 10-dimensional universe, and we only observe this 4, and somehow our observation so far has not reached out to the other 6 dimensions. So the various names have been given to this. This is sort of a way of the non-compact dimensions, sort of as the ADS-CFT correspondence, whereas this is known as the standard compactification scenario. I mean, one analogy to think about this, if I'm looking across my room now, there's an ant on a branch across the street. If I ask I can't see that far, but if I were asked what kind of universe does the ant live in? Well, I will say, well, the ant lives about 1 plus 1 dimensions, right? It's 1 dimension of time and 1 dimension of space along the twig of the branch, right? But if you zoom in a bit, you'll see that it has a curled up extra 2 dimensions. So the ant indeed, the ant indeed lives in 3 plus 1 instead of 1 plus 1. So you have 2 compactified directions. Fine. So in 1985, people realized, and this is the beautiful work of Candelas, Horace, Strominger, and Witten in a joint effort between Princeton and Harvard, which is they realized that these extra 6 extra dimensions aren't just random. You can't just randomly pick 6 dimensions. They must have their own geometrical properties. Right? So one of the things they realized was that this 6 extra dimensions is not just any 6 compact manifold, but it was what's known as a complex threefold, which is Ritchie, Flat, and Kähler. Okay. Now this is a wordful, and don't be discouraged by these random words I've thrown at you, because believe it or not, in 1985, physicists have never heard of these words before, and that's the story I want to emphasize. Physicists have heard of what Ritchie flat means. So Ritchie flat just means something that has 0 curvature. Okay. But what the hell is scalar? And what the hell is a complex threefold? What does that even mean, right? So now let's completely turn off the physics side and turn to mathematics. It just so happens, by then up until in the 1980s, pure mathematicians were thinking about exactly the same, along the same lines of ideas. And this is very, very interesting. So let's go back to Euler, Gauss, and Riemann. Okay, this is classical. You can, Euler's, 17th, 18th century, right? Early 18th century. So what were these guys thinking? Well, Euler gave us this really beautiful theorem, right? He said, if you take a two-dimensional surface, okay, I'm going to take, the technical words can put on this, they're connected, connected, smooth, compact, no punctures, etc. But you can just think about it as smooth surfaces. Well, how many smooth surfaces can it possibly be up to topology? Okay, by topology, I mean, you can just, no cuts and no pasting, just smooth deformations. Euler told us that all such surfaces, if it's orientable, then it's only this family. There is the surface of a sphere that we're familiar with. There's the surface of a donut, and the surface all of the higher donuts. Okay, that's it. Everything that is a surface, which is smooth, compact, orientable, blah, 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 is topologically equivalent to one of these things. Okay, so I mean, I have my cup here, the surface of this cup is continuously deformable to the surface of a sphere. Okay, if my cup had a handle, then I can continuously deform the surface of my cup, your coffee mug, for example, to a donut, et cetera, et cetera. And that's all there is. And this number of holes is what's known as a genus. Okay, so a sphere is a genus 0 object, a torus is a genus 1 object, et cetera, et cetera, et cetera. Okay, fine, that's Gauss, that's Euler. Then come, Gauss and Riemann. Okay, so this is a very interesting fact. Gauss recognized a very beautiful fact. Okay, I won't get into the technical details of this. He realized that if you integrate the curvature along one of these suckers and divide that by 4 pi. In fact, if you integrate the Ricci curvature of one of these surfaces and divide it by 4 pi, you get an integer. Okay, and that integer is exactly 2 minus 2 times the number of holes. And Gauss was so impressed by this fact that he called this his theorema egregium in his own collected works, his great theorem, because it's completely mind-blowing. I do some crazy integral, and it's got cosine, sine, I integrate. At the end of the day, I divide this answer by 4 pi, get an integer. Not only is that an integer, it's an integer which counts exactly the number of holes. And that integer is what now we call the Euler number. And its relation to this genus is 2 minus 2g. Okay, that's fine. And then comes Riemann, right? This is historical progression. What did Riemann do? Riemann says, well, Riemann loved complex numbers. He says, why think about these things as surfaces, as two-dimensional real objects? I prefer to think of them as complex one-dimensional objects, right? So that's the relation between real numbers and complex numbers. A real number, I think about, x and y, every 2 dimensions of a real number, I can, what we mathematicians call, complexify into one complex dimension, right? So Riemann put a structure on these manifolds, and these, in his honor, these called Riemann surfaces or Riemann curves. They're complex one-dimensional objects instead of thinking of them as 2 real dimensional objects. Okay, and then this opened up an entire new dictionary, if you wish, in mathematics. The torus as a Riemann one complex dimensional object is exactly the boundary between something that's positively curved and something that's negatively curved. You can check that the integral of all of the curvature of the sphere is a famously positive curved thing. You get a positive number. If you integrate the curvature on any one of these things, you're going to get a negative obviously thing. And then if you integrate the torus, you're going to get 0 because it's flat. It has 0 curvature. How do you see this? Well, I can just pull myself a piece of paper, right? So I can get a piece of paper. This is a flat piece of paper. I can identify its opposite sides, and now it's a column, right? Or the surface of a column. then identify the surface again. You can convince yourself that's I'm going to get a rubber tire, right? I've been teaching my 6-year-old and my 4-year-old that this is what you should call this the surface of a torus. So the torus is inherently Ricci flat. It comes from a flat sheet. You can't do this to any of the other surfaces. You're going to get cringes. You have to cut, right? So wonderful story of spanning 200 years of pure mathematics. I'm not going to get into any of the details of this, but you have the Euler number in the genus, which belong to the field of topology. You have the integral of curvature. This is what Gauss did, and that's in the field of differential geometry. And they're equal. So mathematicians love equalities, right? So the Theorema Grigium of Gauss links these two fields. And in between, you have this new field called algebraic geometry, which was only settled in the 20th century. But the correct way to think about this is in terms of index theorems and in terms of algebraic geometry. So this is Chern's contribution, and this is Atiyah and Singer's contribution. So this is a beautiful story in complex dimension 1 that dates back to Gauss and Euler. Complex dimension 1 means real dimension 2. Just want to emphasize that. So now let's just all work in complexes over the complex numbers. Now, how do you generalize the story to higher dimension? You want this to be not just a special case. Does it work in every dimension? That's what mathematicians think about. Does it work in an arbitrary dimension? And you can imagine high dimensional geometry in topology is extremely hard. For example, the Poincaré conjecture was only settled by Perelman just a few years ago, 150 years after Poincaré, right? So 100 years after Poincaré. And higher dimensional geometry gets much, much more subtle. Two-dimensional geometry is beautiful and perfect. Nevertheless, for complex and Kähler manifolds, this is a very special class of Kähler manifolds, which Riemann, in some sense, you can show that all Riemann surfaces, these ones, are actually not just complex, they're in fact Kähler. What does Kähler mean? If you want a technical definition, Kähler just means that the metric comes from the double derivative of a scalar potential. That's all that means, okay? So if you put more structure, it's doable. Okay, so fine. So at least for Kähler manifolds, people thought that there's a hope that this beautiful story can be generalized, that we have this control between topology and geometry and differential geometry and algebraic geometry and index theorem. And this was conjectured by Eugenio Calabi in 1954 and to 1957. Okay. Again, this is the technical statement of the theorem. If I read out this technical theorem, you'll fall asleep. So you can read my slides later for anything that's technical. So the point is, for Kähler manifolds, there is an analog of this sequence of equalities, and it's controlled by algebraic geometry of Chern classes. Fine. And this theorem wasn't settled until 1977 to 78. It took 20 years for mathematicians to prove this, that there's, that this kind of structure works in arbitrary dimensions for Kähler manifolds at least. Okay, if not for complex manifold, but for Kähler you have a shot. And then this was proved by Professor Shintong Yao, and for which she was immediately awarded the Fields Medal. So you can see that this is why such an important problem in pure mathematics. This has nothing to do with physics. This just so happens that people are trying to generalize this story of Euler, Gauss, and Riemann, and then Calabi says, well, I can't do this in general, but for Kähler manifolds, I have a shot that that there is this kind of nice control by Chern class. Yao proves it, boom, gets the Fields Medal. Well done, everybody's happy. And it just so happens that Yao was a faculty at the Institute of Advanced Study in the 1980s. And this author, the physicist, Strominger, was visiting the Institute of Advanced Study in Princeton right around about that time. So Strominger went to Yao and says, I stumbled upon this crazy thing. I have a Ricci flat complex manifold whose metric comes from total derivative. What the hell is this? And Yao said, well, I just got the Fields Medal for this. I think I know a couple of things about this, which is fantastic. So in fact, it was the physicists, Candelas, Horowitz, Strominger, and Witten, who named these Calabi-Yau manifolds in honor of these people. So mathematicians are not that inventive. They call these compact Ricci flat Kähler manifolds, not quite as catchy. Calabi-Yau sounds much more catchy. So what is Calabi-Yau? Essentially, you're thinking about the generalization of the torus, the surface of the torus, to arbitrary dimension. Okay, this name, of course, is so. So let me just give you a few examples, right? As I said, in complex dimension 1, there's only the torus. That's it. Okay, the surface, not the donut itself, but the icing on the donut, the chocolate, not the solid one, but the surface of this is complex dimension 1. In complex dimension 2, there are two of these things. There's the 4-dimensional donut, which my daughter loves. So she says, well, if you can eat 2-dimensional donuts, a 4-dimensional donut would be absolutely awesome, like all the chocolate in the world. And there's the other thing called the K3 surface, which I'm not going to get into. There are only two of them. But physicists at the time were thinking about, well, 3-dimensional, complex 3-dimensional things, right? Because 3 times 2 is 6, right? This is our starting point. 10 is equal to, the string theory in 10 dimensions is equal to 4 dimensions of our space-time plus 6. And because of this scalar complex structure, 6 is 3 times 2. So we need to look for 3 complex dimensional things. And incredibly, nobody has even the slightest idea how many there are. Yao didn't know. Yao conjectured that it's a finite in number in topology, but nobody knows. So it's kind of unfortunate that this is a mathematical fact that we don't have a complete classification of threefolds, right? But nevertheless, this whole idea of Calabi-Yau, because of this joint work of Candelas, Horowitz, Strominger, and Witten, in combination with Yao's expertise, grew both in physics and in mathematics by the mid-1980s. Okay. Here's something that's really cool. Chinese gaming developers, I've just only found out about this, have recently written a game called Calabi-Yau. And I don't know, it's like some kind of a shoot up. I'm not a gamer. I don't know. You can apparently buy this. It should come out in January of next year. So if you want to know, like, I don't know, maybe you can throw like Calabi-Yau bombs at people. I have no idea what this game is, but it sounds really cool. I will play a game just for this name. So they did actually get Yao's permission to develop this game. So I encourage people to download from here and, like, I don't know, buy this game and play with it, because hopefully it has like high dimensional geometry built into the game. I have no idea. So let's go back to the a little bit of technical side. So fine, how do you actually construct these Calabi-Yau threefolds, right? These complex 3-dimensional Calabi-Yau things. We don't know. We don't have a classification for them, but at least let's hope we're going to have a shot at trying to construct them. So how do geometers construct shapes? Okay, there are 2 different ways to do it. One is through the branch of differential geometry, where you define everything in terms of intrinsic maps and intrinsic charts and and transition. I mean, it's all technical stuff. But there is another really beautiful way to construct shapes that go back to when we were in kindergarten. And that's a field called algebraic geometry. I mean, your teacher may not have told you this, but your teacher would have should have told you what you were actually doing is a baby version of algebraic geometry. So for example, if I realize p squared plus q squared minus 1 equal to 0, this is the vanishing set of points defined by a polynomial, right? And we know what that is. We remember from this when we were 6, this is a circle, right? The vanishing locus of the points of this polynomial is called a circle. Fine. And that's all algebraic geometry is, to try to model shapes in arbitrary dimension by defining them to be vanishing sets of polynomials, or multiple polynomials in multiple variables in arbitrary dimension. And one technical side is that we don't as algebraic geometers, we don't like to work in real space. We like to work in complex space, because we are working over complexes, over the complex numbers. In addition, we like to work over what's known as a projective complex space. Why do we like projective space? What projective space means is basically means you take the point at infinity and you bring it in. You include the point at infinity in, so everything becomes compact. Okay. So here's a nice theorem. This is a very powerful theorem. Theorem number 1, I actually didn't put this down. Any Kähler manifold in any dimension can be realized as vanishing sets of polynomials in multiple degrees, in multiple variables in projective space. That's a theorem. Okay. In particular, theorem number 2 that if you take a homogeneous degree n polynomial, of n plus 1 polynomial in this n-dimensional complex projective space, you get a Clavier. Okay, so that's a nice theorem that at least gives us a construction. This is not very abstract, but at least in dimension 1, you can plot these things, and I encourage people to plot it. If you take this as, just literally take this, take x, y, z as complex numbers, and write down the vanishing cubic, the set of points, split them up, take x, y, z, and split them up into real and imaginary parts, and then solve this this complex constraint, which is 2 real constraints. So I think that should work. And just plot Monte Carlo this point. You're going to see the surface of a torus is emerging from this plot. That's kind of fun. In mathematics, this thing is called an elliptic curve, which is my favorite thing on the planet, because that is crucial. It's one of the most crucial things in algebraic geometry and in number theory. I'm going to mention a little bit of that later. From Andrew Wiles' famous proof of Fermat's last theorem relies on the recognition of this fact that the elliptic curve is this Clavier one manifold in some sense. Okay, back to physics, or this is just pure math, right? So this is so fun, right? I'm never bored because I'm constantly jumping between 3 different fields, and I've learned the trick. When a math conference invites me, I say I'm a physicist and a computer scientist, and every combination I'm saying I'm the other guy. And a computer science conference invites me, I say I am a mathematical physicist, whatever. And then people say, like, if they will pardon any ignorance that you may say. So this is kind of fun. So I'm just constantly not bored, and I'm jumping between fields. So let's get back to physics. So one of the early questions that physicists asked, namely Candelas, Horowitz, Stroman, and Witten asked Yao, it was not just how to construct these things, but it's not just random Clavier manifolds. I need something that, in which the physics makes sense. I need 3 generations of particles. That's what CERN tells me. There are exactly 3 fundamental generations of particles, right? If you think about it, so everybody knows what an electron is, but the electron comes with two family members. There's the electron, the muon, and the tauon. It just so happens that every elementary particle comes with the number 3. We have no idea. There's still no theoretical explanation. It's just an observational fact of nature. Whenever there's a fundamental particle, it comes in 3 generations, except the Higgs. It's a crazy structure the Standard Model has, right? But it is what it is. So neutrinos, right? Neutrinos come also in 3 families of flavors. There's electron neutrino, there's the tauon neutrino, there's the muon neutrino. Why? Nobody knows. So this 3 gets translated to this beautiful question back in the mid-1980s, that the Euler number, this thing that I introduced you, the number of holes for this Clavier is equal to plus minus 6. As far as I know, this is the only sort of mathematical explanation, if you wish. Of course, it doesn't explain, it translates one problem to another, but in some sense, it's a mathematical window towards this generation problem. Why do we live in this universe that has 3 generations of particles? No idea. But at least here's a shot at it. You've translated this problem to pure geometry. So, fine. And then the entire, I'm not going to bore you with the details, but then the entire 20 years of effort, of combined effort between mathematicians and physicists, just trying to construct these things, which could try to answer analog of this question. Okay, so some kind of a topology or a pure geometry of these shapes, which control what the basic, what the property of the universe is. And what I should make all kinds of, I can sit and over it's almost Christmas, over a log fire and some marshmallows and a good bottle of cognac, I can tell you this 20 years of story. But I'm gonna save that for some Christmas when I'm old. But the main point I want to emphasize that physicists actually turn to actually construct these things, right? So a typical thing is some matrix configurations of degrees in polynomials. You can record these shapes in very precise combinatorial terms. Okay. The most impressive work was this work undertaken by Kreutzer and Schaka in this Viennese collaboration. They took 10 years and they found 473 million Clavier manifolds. Okay, this is respectable, a huge size, right? Suddenly, we went from like a handful, maybe 8,000 by the end of 1990, to this incredible number by the turn of this century, exactly this turn of this millennium. They came up with this number, 473 million. Now we've got plenty to play with. Yau's conjecture, of course, is that this number is finite, but it's a strange sequence, right? Here you got 1 in dimension 1, 2 in dimension 2. You would imagine 3 in dimension 3. No, but in dimension 3, suddenly you have at least 473 million, 500 and 486. At least that's the lower bound. It was many, much more, but it's finite conjecture. Strange sequence in mathematics, but mathematics has surprises for us. So here's something I ripped off from the internet, which is technically the age of data science is much earlier than you think in mathematics, right? In even 20 years ago, this was sort of beginning to emerge into the physics community and the mathematics community, right? So yeah, I love this quote. This is just awesome. This is a great way to, well, I don't know, this, I have to consult with my theologian friends here in Oxford whether this is considered heretical or not, but I don't know. My father-in-law is very much a theologian, so I have to consult him whether this image is considered heretical. Anyhow, moving on. So in this book, I think that Ryan mentioned in the beginning, which, gosh, I mean, took me 2 years from the first draft to now. Hopefully, it'll appear this year. This is my quarantine project, which is to finally get this. So I tried to summarize all of the stuff that's been done in the past 40 years in this dialogue between mathematics and physics and now data science called Clavier Landscape. So just to take stock, I think whatever string theory is, it's a very nice realization to this ancient question or ancient proposition that Johannes Kepler gave, which is, he said this famous quote, where there is matter, there is geometry. This is very prophetic. Of course, Kepler was saying this purely from a philosophical point of view, but whatever 20th century, 20th and 21st century mathematical physics is concerned, this is a great realization because, you choose different shapes for this extra dimension, you get a different universe. Some universes may have 15 generations of particles. Some universes may not have the electron, but you select one of these shapes, you get a new one. You get a select, you get, but now we have hundreds of millions of possible selections to do, okay? So at this point, first of all, I'm completely agnostic about string theory. Whether it is a theory of fundamental nature, I don't know. And second of all, I'm completely agnostic about whether our universe is special in terms from a geometrical point of view. I mean, there are 3 philosophies you could take. One, our universe is probabilistic. We just happen to be in this universe, which supported the solar system, which supported Earth, and we happen to be alive. That's to ask the question. That's the anthropic principle. 2, you can say, well, there's something special that selects for 3 generations of particles, that selects for 1 Higgs, that has this mass for the quark, blah, 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 blah. That's a special selection principle of the universe. And I wrote a paper with Candelas. I was very happy to have written this paper with Candelas, who's one of the pioneering fathers of this field. And is it possible that our universe is special, right? So we named this triadophilia from the Greek for the love of 3. Whether there are geometries which select threeness. And some initial experiments that we did, or some work that I was doing in postdoc at University of Pennsylvania, we found that we're not searching through null sets. It's conceivable that our universe is special, and we can tune special shapes to find our particular universe. I like to compare this field to the exoplanet search, right? What is the exoplanet search? We're looking for the habitable zone, and I think the current exoplanet search has scanned through 10 to the 21 possible solar systems, and we find about 10 to the 3rd, about 1,000, which are sort of in the Goldilocks zone of planets. What we're doing is something much more, I think, much grander, We're looking for possible universes which could support anything that is akin to our universe in the within the possible compactification of all possible geometries. So fine. Meanwhile, but by the turn of the 21st century, this 473 million grew to be much, 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 much larger. This is because what I described to you was just one particular dual equivalent formalism of string theory. Then with all of these works here, there are other equivalent formulations of string theory, and there are different geometries you can turn to. So the Calabi-Yau landscape, as big as it is only a small corner of possible geometries and non-geometries that you can reach our universe. So numbers like 10 to the 500 are beginning to float around, even in the beginning of this millennium. So this 10 to the 500, by the way, is a very much back of the envelope calculation estimated by KKLT and Douglas. What they basically did is, well, let's roughly estimate how many possible Calabi-Yaus there are and how many cycles there are. So it's a very rough idea, but it's a huge number. It's absolutely enormous, right? So this is called the vacuum degeneracy problem in string theory. How do we solve this problem? Right? There are just too many possible ways to reach our universe. Yes, I know it is true that it's very rare to get our universe, but even if the chances of hitting a random universe like ours is 1 in 10 trillion, there's still trillions upon trillions of possible universes that could look like ours. So where do you take your philosophy? So in some sense, string theory trades one very difficult problem, which is the quantization of gravity, by another very interesting problem, which is to look for the right geometry. And to me, the second one is a much more interesting problem. I don't really think about whether string theory is the theory of everything. What is most interesting to me for string theory is that it's a dialogue generator. It has broad fields of expertise in the last 30 years, especially, of people who would otherwise never have been seen in the same room before. And this is a very exciting thing. Personally, I think, every time you get a field that does this, there's got to be some truth to it. So here's the diagram. So if you plot the major breakthroughs in the history of mathematical physics in terms of theoretical physics, right? Riemann predated Einstein for about 60 years. So M is blue, P is orange. And Dirac, every one of these, so everything in black here is the major Nobel-winning thing that completely changed the paradigm of physics. And you could see that they're all based on mathematical ideas that preceded them until today. And you can see this lag getting closer and closer and closer. And we're pretty much at an intersecting point exactly right now, where Fields medals are beginning to be given to physicists. Witten is the first physicist to be given the Fields medal. He was using supersymmetry and quantum field theory to understand a pure problem in geometry. This is kind of, last time something like this happened was Newton, right? I mean, you could argue. So it's kind of interesting to see this lag. And so for me, this is the most important. This is the reason why whatever I do is sort of stringy related, because it provides this dialogue between mathematics and physics. So again, let me take stock. Let me just see how good my time is. How am I doing on time? Okay, good. Gosh. Okay, so okay, fine. I got about 10 minutes. So what's good? So in the past 10 to 15 years, mathematicians and physicists have started talking to the greater community of computational mathematicians, computer scientists, right? That's the good. The bad thing is that any of the algorithms needed to compute anything is computationally complexity hard. If you want to, do any of the detailed computations, it's actually double exponential. So you can't just, punch in 10 to the whatever data and just let some supercomputer run and say, well, end of the day, I'm going to say, well, that's like a SETI search in a way, right? You're randomly scanning through the sky, and can we ever find intelligent life? I don't know. I mean, it's a very complex problem. So a natural question to ask is that, can we borrow techniques from this big data? What characterizes the 21st century? And in fact, in particular, this decade of the 21st century is the big data revolution. AI research. So that's what got me thinking in 2017, which is, the typical problem in string theory is, and in algebraic geometry for that matter, is to take some some input, whether it's some complicated tensor input or whatever, and at the end of the day, it's computing some topological invariant, right? And which can be interpreted into properties about our universe. So in 2017, I was asking this question, can we machine learn this landscape? Can we use AI to help us do mathematics with machine learning, right? So that was detailed in this paper. So it's kind of interesting, and I was very surprised that this kind of experiment was actually doable in geometry. And interestingly, I have to mention that several of my colleagues have been thinking along. 2017 is a great line. It had a great year. It's the year that people were thinking about this AI research, and it's the year that Sophia became the first non-human citizen of Saudi Arabia. So that's kind of it's in the air somehow. So, but my take fundamentally is what can we do with this in terms of mathematics? So just here's what I mean. Probably this audience knows something about machine learning, but I'm just going to give 1 minute about it. So if you throw this handwriting digits recognition problem to a mathematician, what would a mathematician do? Mathematician will go crazy. We try to find clever Morse functions, topological invariants. Let's see, what's this and this, right? But of course, that's not what Google does, right? Google takes NIST, represents these as images, and trains some supervised neural network. That's what Google does, right? So what is I won't have time to go into the details of machine learning, but basically, I mean, for one neuron, the perceptron, this whole thing started in 1960, and that's kind of crazy. That it's just nonlinear regression. Oh, by the way, I should have edited out some random Chinese words here. I was giving a lecture about machine learning in China, so I should have. Anyhow, you get the extra benefit of learning what all these words are in Chinese as well. So the emergence of complexity for machine learning is to establish things like neural networks, which each neuron or activation function of which is doing some kind of nonlinear regression. And it's this connectivism which emerges complexity. Right? So that's my one minute on machine learning. So what does machine learning do? It takes images and processes them and finds some optimal weights and optimal biases, which will, at the end of the day, predict that this matrix should be associated with a number 3. Okay, this is supervised machine learning in a nutshell. Well, what I thought about in 2017 is, well, how different is that from the computation of topological invariants? Here's a representation of a manifold, doesn't matter what it is, and I know how to compute from here to here. Okay, the proper way to do it is to chase sequences until you're blue in the face. This is, I don't know, 4 years of undergraduate mathematics plus 2 more years of graduate work in mathematics will make you finally understand how to compute from here to here. But at the end of the day, people have computed it. As I said, people work for 20, 30 years to collect this large database of this computation. There are no particular rules and no particular, well, yes, there's an algorithm which does it, and it's an expensive algorithm. It's a double exponential running algorithm to do this. But we know, as a community, we've bitten the bullet and actually computed it. But at the end of the day, this is where I reap the fruit of harvest. How different is this from the recognition that this image is to be associated with the number 8? That's it. So throwing in some neural network, and that's exactly what I did. And it's predicting this number extremely well. And then with my various collaborators and my students, and then some more refined work done more recently, you can get up to 99.99% accuracy for predicting this kind of computation. And this story is great. There's now an entire program in the string community since 2017 that people are doing, trying to understand and compute how to help with the computation of finding universes based on the previous experience of geometry and theoretical physics. And there's been some very daring proposals. There's Hashimoto and Halverson and friends that were thinking about, maybe the universe itself is some kind of a neural network. And that's much more drastic interpretation of this. So in some sense, this reminds me of this wonderful thing which a friend of mine just sent me yesterday. You probably all seen baby versions of this, but this is actually a correct version using some pretty high power mathematics, which is actually, this is exactly the kind of mathematics that you do. I mean, the stuff, my research is precisely about cohomology over polynomial rings. And this, you can actually work it out at the end of the day, what the donut is equal to, or what this hot dog or this burger. And in some sense, this machine learning is doing exactly this. I mean, it doesn't know what symbols to use. It's using some optimal sets of symbols, call it hamburgers if you want, to try to approximate the experience of mathematical research that we've done in the past 30, 40 years. And this is where I envision where this is very much going. And so this is sort of the program that I'm trying to launch, which is, can you machine learn mathematics itself? Why stops the string theory and geometry, right? So playing around, what about algebra? Let me see my time again, so that, oh great, I have some time to tell you about some of the experiments I've been doing. Forget about geometry, forget about string theory. What about the fundamental tenets of mathematics? So one of the central problems in algebra is the recognition of a finite simple group. Now, a group is an abstract object. A simple group is a building block of a group. And in some sense, a simple group is the analog of prime numbers for groups. It's not easy to just, you show me some multiplication table of a group to recognize whether it's simple or not. It's a very strange way to do representation theory. Nevertheless, if you feed this into a neural network, it's very quickly adapting and finding, using a support vector machine, that simple groups can somewhat be distinguished. So this is very much still work in progress. This is our preliminary preprint. I've done this with Min-Young Kim, who is one of the world leaders in number theory. But this is a very, very strange thing to do. And if true, it would potentially raise shocking conjectures that if you plot the finite groups in some big high dimensional space, you can separate them out, the simple ones from the non-simple ones. Kind of crazy, right? Similarly, you can do this with, I've done this with collaborators here, and then you can do this. It seems that you can use Lie groups, continuous groups. You can have similar properties. What about other branches of mathematics? What about combinatorics and graph theory? So various experiments I won't bore you with, but the funnest experiment is this paper that I just wrote in June with Yao himself. So I'm very glad that the founding father of this field is himself interested in this machine learning approach to mathematics. So my other job is now to convert candelas. Then I will get all the founding fathers together and convert them to this field. So, I mean, as I said, in this earlier paper that I had with Philip Candelas, it was Philip is old school, right? He wants to understand things from a selection rule. Right? This kind of experimentation would take some more time to tune him to. But anyway, Yao was very excited about this. So we did some simple experiments. Our motivation is a very technical one. It's got to do with graph Laplacians. But at the end of the day, can you distinguish just by looking at the adjacency of a graph, whether it's cyclic, planar, whether they exist Hamiltonian cycles? Luckily, there's a database that Wolfram tried to collect over the, has over 10,000 graphs, every known one since the 1970s, and all of the properties are known. You just train a neural network to see whether it has these properties which are immediately recognizable. The good thing about this is that, the computation time to everything, we're guessing, right? This is what mathematicians like to guess. This is guesstimation. And it's guessing within seconds, because it's not doing anything. It's not doing any of the expensive computation. And at some point, it will start guessing correct things. And this has already happened. So just to mention, there's this paper of Brody, Konstantin, Lucas, my friends. They actually guessed the correct formula for cohomology. And recently, we're formulating some precise conjectures in number theory using this approach. So let me finish with this. So you would imagine that this machine learning approach of doing mathematics will break down in hard problems in number theory. We know there are no patterns in primes. if I can start using a neural network to predict what the next prime number is, I won't be sitting here today, right? Because I would be breaking every single bank in the world, embezzled all of the funds, and then run off and bought myself an island. The fact that I haven't done this means that my experiments, my initial neural network experiments with prime numbers have not worked. And this, unfortunate this is for me and my family, this is very actually reassuring for me as a mathematician, because we know that number theory is hard. There are random patterns in primes. You can't. It's very difficult from a mathematical, from a logical point of view, trying to find patterns in primes that have not been discovered. So, and yet, surprisingly, just in the last couple of months, we find that some branches of number theory, like arithmetic geometry, this is very much Andrew Wiles and Min-Young Kim territory, behave very well. You can predict properties of elliptic curves to sometimes up to greater than 99% accuracy. So we're trying to improve this. Once we get this to 100, which is not inconceivable, then we can make a very precise conjectures in sort of arithmetic number theory. But hard primes, if you just hit primes themselves, probably you won't have much luck. And it's good for mathematics and bad for my bank account, because if I can do that, hey, just start breaking every bank. So good. So I think my time is up. So let me just summarize here. Obviously, this idea of using machine learning techniques is valuable to physics, because all of a sudden we can start not just sift through universes, but we can statistically estimate and zoom in on regions of possible universes that we should be looking for. So that's, for physics, it's great. For pure mathematics, and this is something I'm thinking more these days, this is kind of very interesting, because this is a potential to, one, find predictors and classifiers of mathematical data, right? Predictors are great because you can raise new conjectures, right? This is already beginning to happen. And also, it's stochastically trying to do NP hard problems, like traveling salesman. So sure, I can't solve it, but if 99% of the time I can solve it, then for applied mathematicians, that's very good. Right? So it's a win-win situation. And somehow I'm trying to map out different regions of mathematics with different branches of mathematics in how difficult they would be in terms of being machine learned. And I think numerical analysis is probably the easiest. Geometry over the complex numbers, somewhere in the middle, and number theory is imaginably the most difficult. So this kind of approach, there are now various collaborations in the world trying to understand different branches of physics and mathematics where you can try to machine learn symbolic manipulations and et cetera. And I think we're still very much at least the paradigm that I'm proposing here is very much in the AlphaGo stage, where your computer, your Deep Blue or whatever it is that has been, not Deep Blue, Alpha, has looked at 10 billion games of Go and is trying to extrapolate some rule. But we are now just at the cusp of the AlphaZero stage, where you're just taught the rules of Go, and then you play against yourself to try to find the optimal strategy. And I think in some sense, mathematics can be done in this way as well. And this is very much Voevodsky and just this last year's International Congress address by Davenport and Buzzard are thinking, it's this automated theorem proving techniques we're using machines to check theorems and generate theorems is probably the right way to the future. And I like this. I like how my friend, who is a professor of logic here at Merton, he says, you're trying syntax without semantics. It is only natural that you go into the semantics of mathematics as the next natural stage. So I conclude with three quotes. The first one is, people say that string theory is a piece of the 21st century physics that happened to fall into the 20th century. Witten has famously said that it's the 20th century of mathematics that happens to begin in the 20th century. And my friend Al Kazberzik has this great way. He says, whatever string theory is leading us as a community, letting AI and machine learning to do mathematics could well be the standard for the 22nd century. So thank you very much for your attention.
Oh, I'm on. Okay. Thank you very much, Professor Yang. That was extremely interesting, and I'm sure that everyone has got a lot out of the talk. Do we have any time for questions, or what do you think, Professor?
Sure. Yeah, I got time if people are around.
Cool. So, well, some questions written down. Just the first one is about the idea of a theory of everything. Do you think that there's more promise in the field of loop quantum gravity or string theory?
Oh, first of all, my disclaimer is that I'm not really qualified to judge.
Okay.
But I know there's a community of loop quantum gravity who tries to, try to do from a completely different, this non-high dimensional approach, and it's very interesting. But the field of loop quantum gravity is much smaller, much smaller, and I think from my perspective, I know the reason why it is smaller is because loop quantum gravity, I don't know, whatever it is as a theory of physics, has not generated new mathematics. Whereas the string theory community has generated new mathematics. I mean, not just using fancy math. I know loop quantum gravity uses a lot of really fancy mathematics, but string theory has generated new ideas and transformative ideas in mathematics, such as mirror symmetry. There are now entire communities of algebraic geometers devoted to studying this mirror phenomenon, which came out from purely studying physics, conformal field theories and string theory, and it's solving new classes of problems. And this is consistently so for the field of string theory. So from this perspective, my gut feeling is that whatever string theory is, as a theory of fundamental theory of everything, it's more likely to be on the right track.
Okay, thank you. We have a question from Mijas. So if you want to turn on your mic, you can ask your question.
Hello, sir. Hello, hi, I'm from Nepal. I'm Mijas Tiwari. And what I would like to ask is about the existence of strings that you stated might be in the black hole. That you have stated on explaining about the strings, that if possible, we can see the strings in black hole. How is that possible? Can you explain me the physics behind that?
Right. So if I understand the question is, whether we could start seeing strings in black holes.
Yes, sir. Yes.
Right. Yeah, that's an extremely good question. And as far as I know, actually, I think there are colleagues who do sort of stringy cosmology. So I mean, obviously, it's very difficult to measure, to go to the center of our galaxy and try to find this black hole. But nevertheless, there is something even better than the black hole, which is namely the black hole at the beginning of the Big Bang. And so my colleagues are actually looking for signatures from the cosmic microwave background and trying to find non-Gaussianities. And it says that's not predicted by standard cosmology, because this is imprinted everywhere in the universe. They're trying to find how compatible that is from a string theory that would have been valid in the beginning of the Big Bang. And this is very much an active field, actually. And my gut feeling is that we're not going to be able to build a machine at CERN or in this new accelerator in China to see strings, because this is so many orders of magnitude higher than what we have now. Nevertheless, the universe itself has that accelerator, and it's the Big Bang, and it's observable everywhere. And I think and this is probably the right way to go. And this is why this gravitational wave thing is so important this year, because in 2018, it's because pure gravity allows cosmology a new window farther back into the beginning of the universe, beyond this opaque era of electromagnetic plasma, but actually to probe much earlier in the universe. And I hope that with this new gravitational wave technology, we can measure much closer to the Big Bang, and hopefully we'll see signatures of string theory there.
Okay, thank you, sir. And I do have one more question. If can I ask? Okay. I don't know the exact time, but a few days earlier, Wolfram stated about the description of theory of everything using machine learning. Do you have any opinion on that? I mean, can you
I
explain?
wasn't sorry. What is this? What is this work? I wasn't aware that there's a.
Okay, I will say it again, sir.
Okay, sorry. I don't know if this. Just a few days ago.
Yes, yes, few days ago, Wolfram, Stephen Wolfram.
Mm-hmm.
Yes.
Okay. Yeah. Sorry. Yeah. I don't. I mean, I'm a big fan of Wolfram, but I don't know what. So he it's slightly different. So what he's proposing is the theory of everything from cellular automaton, where he tries to generate all of the rules from physics from the underlying from some underlying simple rules of automaton. I think it's a very, very interesting idea. And the physics community, however, hasn't been that receptive about it. So you can go to blogs where the high energy theory community and the string community, you can read their critique on why they think this may not be the case. But for me, I mean, from a computational point of view, I think this is a wonderful idea.
Okay, thank you, sir.
Yeah, thank you, Mijas. So the next question we have is, new theories of mathematics, do you think that they will, is there something about mathematics that will mean that can always be applied? And I guess this is moving it in a more general philosophical sense. Do you personally think that maths is discovered or invented?
Oh, well, see, I'm a Platonist. So I think mathematics is always there, and all of physical reality is just a manifestation of mathematics. I guess I'm a pretty extreme in this view. I think any beautiful mathematical structure will find its place in the physical universe.
So we have a question from one of our members, Rajarshi. So I think he's going to turn on his mic.
Hi, Rajesh here.
He's actually in the same room as me, so why don't you come over here, Rajarshi?
Okay.
Apologies for the blast of feedback there.
Hi, so Rajesh here.
Hey.
So hi. So what do you think is like the future of number theory? Like nowadays, as you're one of the people who are connecting fields of like number theory with like AI and stuff. So what do you think there is for the future of like the whole of number theory in general?
Oh gosh, wow, that's a very hard question. So my colleague Min-Young Kim, and who is a big proponent. Actually, he would be a great guy to invite to give a talk on this. He has been a big component, a big proponent in combining physics with number theory. You think this will never meet, but he borrows ideas from physics to try to solve hard problems in number theory, and vice versa. Of course, you can imagine always happens. So you can always do some physical system. And so that's why I was so excited to have written this algebra paper with Professor Kim. I think it's promising. I didn't think that this was going to be promising because, if you do hard primes, like I was going in this slide here, it was just giving a completely random prediction. So this is something I didn't mention, was, if you train a neural network on a sliding window to predict whether the next number has an even number of prime factors and odd number of prime factors, it's as good as a 0.5 random guess, which is good. That's kind of reassuring. But I was very surprised that you can get many non-trivial results from things like arithmetic curves, and you are predicting much more precise nuances about refined problems in number theory. And I think this is very, very new. So we've been in touch with LMF. So I highly encourage you to go to LMFDB, which is this database of L functions and modular forms maintained by Sutherland and friends at MIT. And so we've been writing with this because this is such a crazy way to do number theory. He says, well, it's a natural way to approach it. And hopefully we'll conjecture with these things. So to quote, so my friends Kyu-Hwan Lee and Tom Oliver are, they're hardcore number theory. They're professional number theorists. And I like to quote Kyu-Hwan Lee. He says, I asked him this question, is it possible that the human eye can raise fundamental and really deep and hard conjectures in number theory anymore, right? Back in the day, like Gauss, right? Gauss did this, right? Now, what was the best neural network of the 18th century? It was the brain of Gauss, right? Gauss said, I plot the primes here. I look at the number of primes less than x. And he was 15 when he looked at this, and he says, oh, it looks like this is x over log x, just because he's a really, really, really clever guy. And then Birch, Swinnerton, and Dyer, which I mentioned in this exploration, they did the first computer experiment, and they were able to raise this problem, relation with elliptic curves and the rank of elliptic curves and the number of rational points on the elliptic curves. And they deployed all this computing in the 1960s, which is a crazy thing. And they raised one of the Millennium Prize problems. So I ask Johan, do you think that today, in the number theory community, do people sit around and try to look at data and try to predict something as profound as Birch, Swinnerton, Dyer conjecture or the prime number theory theorem? And Kuan says, no, this is just not possible anymore because we would have guessed, we would have missed it. The only natural way now, he thinks, to do this is to let machine learning, some kind of some supervised or unsupervised machine learning, just to go through this data and notice more exotic patterns and then raise conjecture. And that's exactly something we're working on now.
Thank you. Thank you.
So we have a couple of questions on AI. So the first one is, do you think that AI will be in the future sort of integral to coming up with any theory of everything? And I think there's a question from Dhruv, I think it's pronounced, in the chat. So if he wants to turn on his mic, he can maybe add to that.
Right. Okay. So about that AI, yeah. Absolutely. Both in terms of, so it's interesting. In 2017, a new annual conference has been launched in the string community called String Data. I had a plot about the annual conferences, but now it's an annual conference where there's an entire community now try to use AI and machine learning techniques to do this problem. And to sift through universes, if you wish, in layman's terms. But that's precise problems. So the physics community is definitely catching on this. And of course, I want to emphasize, this is nothing new for the experimental physics community. The experimentalists have been using AI for 20, 30 years. It's particularly interesting. I asked a guy on the team who discovered the Higgs boson in 2014. I asked him, point blank, do you think the Higgs could have been discovered without machine learning? Right? And the guy said, absolutely not. It is impossible to discover new particles or to do any fundamental theoretical physics, experimental physics at this point without machine learning. Because, if you think about it, back in the day, in the 1960s, they discovered particles by looking at bubble chambers. And, they got like some poor graduate students to stare at this, photo plates. And, the graduate student looks through maybe 1,000 of these plates, gets pretty sick, and say, oh, wait, there's a little curl over there, right? But that's not how they discovered Higgs. They discovered Higgs by putting every single image, we're talking about billions of images of all possible cloud chambers in all possible previous, supervised training that and see whether you can detect anomalous passages. And they found Higgs exactly by one of these things. So this is, I think it's almost unthinkable now that fundamental science is going to be decoupled from, this is going to be obviously the most important tool. What is surprising to me is that mathematics can benefit from this kind of research, and that's more surprising. This is why I've been trying to push this program so passionately, which is the same thing. As mathematicians, we don't sit around and say, we formulate some people do, but not all of us sit around and say, well, I'm going to formulate some very abstract structure. And then from this, I deduce this. And that's certainly not how historically it's done. Mathematics are done by a lot of experimentation that we don't tell people about. We do it in our bathroom, we run in a bath, but we don't admit that in public. We say, we present a beautifully woven story. But, it's like Gauss, when he was 15, he was just say, oh, let's plot a couple of these things and see how prime numbers progress. And that led to a 100-year-old conjecture, which was only proven later. So I think it's a very much similar thing today.
Okay. If Dhruv is there, he can turn on his mic, but
Hello, sir. I'm Dhruva from India, and I have
Hello.
a very weird question. The quantum computers, as you have heard, are popping up everywhere. What is your review on them based on computational number theory? And also, they are told to be simulating nature itself. So now nature can be called in numbers. So what is your view on that?
Oh gosh, that's a deep question. I don't know. I think I'm agnostic at this point. Whether there are all these different components of reality as simulation, that kind of thing, or simulated reality. Do we live in a computer algorithm? At some fundamental level, and how much can we program in? I mean, there are two levels. Where there's that simulated reality level, and then there's the other level of how much can we get out by punching in the fundamental rules of arithmetic. And I think that's sort of, I think your question is probably leaning more towards the second one. I think that's very much a direction. This is what I said about this AlphaZero approach. It's happening even in this. I mean, it's really started in the last year or so in the math community, where you punch in the axioms and you let the computer run itself to generate a proof. And this is doable in a very complicated way. So even Mathematica has a built-in automated theorem prover. I can punch in like Leibniz for differentiation and integration parts, and then you could prove some simple rules. But the proofs are incomprehensible. It's like 50 lines of logical symbols, which are completely correct. But what we're hoping with this injection of machine learning is that at least we'll go towards more of a direction of intelligible statements. I think this is what Max Tegmark calls intelligible intelligence. You want to understand what the AI is doing, how it's optimizing certain steps and certain proofs or certain steps in computation. I think that's a very meaningful way to do. And I think this is certainly the case with number theory. And that's what I've been doing with Q-Hwan Lee and Tom Oliver, which is it's fine. Okay, we're getting neural networks to predict to 99% accuracy. But once we hit 100%, we want to untangle all of the activating functions and make a statement. Why is it doing in terms of finite number of symbols? And I think this will be very, very useful to number theory research.
Yes, sir. It is a very interesting field to explore, and even quantum computings are now giving us an acceleration in the computational
That's
field.
right. That's right. I haven't even mentioned quantum machine learning. I don't know how to get into it, but first we need to get a very good working quantum computer to.
Yes, sir. IBM is trying, and everyone is. Yes.
Right.
It was really good talking to you. Thank you.
Thank you.
so yeah, I guess the follow-up to the talk of AI is what do you think about this notion that AI poses some existential danger to humanity?
And it's always like the singularity.
Yeah.
No, I welcome it. Obviously, I don't think eliminate humanity, because I think we're a smart and pretty resilient species. I think we'll find. I think, and I certainly hope that humanity will find the best and optimal interaction with AI. And in fact, I think reminded Lord Martin Rees, who is the Astronomer Royal, had made years ago a very good comment. He said, we're looking for all this organic life out there in the exoplanets and this, that, and the other thing. Why aren't we looking for AI, intelligent AI? It could well be that any civilization that's advanced enough will have downloaded itself onto AI to make itself survive. And I think that's a very optimistic way of looking at this problem. I think we're depleting our own natural resources, and our nearest planet, our nearest system, solar system, is certainly very far away. And it's not unimaginable that we will use up all our resources before we can successfully colonize another planet, in which case we should put our efforts into finding AI into which we can download our collected consciousness, if you wish, as a species. That's a very meaningful thing to do.
So I think we'll wrap it up pretty soon. We've got a question from Devyans. So Devyans, if you could turn on your mic, we can have that. Oh, or I've just been told that I don't think he's here. So I think we'll wrap it up then. So thank you again, Professor Yang, and answering all of our questions. So yeah, thank you everyone in the chat for coming along. And I'll just say again, we're going to be running a winter series in quantum field theory within the next couple of months. So everyone, please keep your eyes on our social media, and we shall be updating you on future events very soon. So thanks everyone for coming along, and we are for science, you know.
Absolutely, absolutely.
Okay.
Great
thanks.
job, guys. Right, thank you.